Hi, this is Mia Reyes. I'm explaining question 2 for exam 2 for Orgo 1 with Dr. Rabago Smith. I have my answer on the iPad here. I'm just going to go ahead and walk through the question and explain each of my answers to it. So, to start, identify the electrophile and the nucleophile. So, we know that this group in the middle with the oxygen here is going to be the nucleophile / base. We see the negative charge, which immediately indicates that it's going to be a base. And we know that the negative charge is going to make it a nucleophile because that negative charge is going to want to find a positive charge. It loves positive charges, so that way it can stabilize. Therefore, this over here will be the electrophile because once this leaving group heads out, this carbon here is going to be positively charged. It will be a carbocation, and that will make an electrophile because it's going to love electrons. It's going to want electrons to come to it so it can stabilize. Next part, what the type of substrate it is. It is primary, and that is because there's only one carbon here that it is attached to. This is obviously a different group. That's a hydrogen isotope, and then there's a hydrogen in the front, and so that leaves only one carbon, so it's a primary substrate. Is there heat? No, there is not. What type of leaving group is a substrate, or what type of solvent is used first? It is aprotic, because there is no hydrogen that is going to leave. There is no proton or anything. It just has the negative charge on the oxygen, so it is aprotic. What type of leaving group is the substrate? It is a good leaving group. We were told in class that MS is a good leaving group, and so I am just running with that. Therefore, this is going to be an SN2 reaction, because since the base is aprotic, it is going to be strong. And then since it is a primary substrate, we can reference our little chart that we had in class, and that will tell us it is an SN2 reaction. So it will happen in 2 parts, which we will see later on the energy diagram and throughout the reaction. So, can there be a carbocation rearrangement? Yes, this is true. Once this guy heads out, it's going to want to become more stable. Secondary or tertiary is best. We can only get secondary over here. There is going to be a hydride shift, and that's going to be when one of these hydrogens shifts here where it is missing where the positive charge is. So now this will become the carbocation down here, so it'll be 1, 2 secondary, which makes it more stable. So draw the mechanism for this reaction and the product. As we can see, this leaving group heads on out. We see it over here. I'm tapping into stuff here. It heads on out over here. We see the carbocation rearrangement where this positive charge is going to move over here and this hydrogen is going to move down here. If we keep following our reaction, we will head down here where we will see that this negatively charged oxygen group will head all the way up to the carbocation. You can follow with the arrow, giving us these 2 products, E and F. Now, draw the energy diagram. Down here, I've labeled them. As you can see, we have A, B, C, D, E, and F. A is obviously going to be at the lowest because it is the starting solution, so it's going to be all the way down here. We're going to have one peak with a transition state, and then we're going to have C and D, where these hydride shifts take place over here. And then the second part of the reaction will be a little bit lower than the first as it goes. And then we will end up with E and F, which are enantiomers of each other because there is chirality where this carbocation is once the oxygen group attaches. What would happen to the rate of the reaction if the concentration of the nucleophile / base was decreased 3 times? Well, the rate of the entire reaction would decrease by 3 times because we know that the rate of the reaction for SN2 is K times the rate of the reaction for the electrophile times the rate of the reaction for the nucleophile. So this is decreased 3 times. The whole thing is going to decrease 3 times. And also, this works out because it is an SN2. If it were an SN1 reaction, the nucleophile would not take any role in the reaction, or in the rate at least. Now, if there's more than one product obtained, explain the relationship. So, as I explained, these are enantiomers, which we know because there is chirality right here where this carbocation was, so this can be in the front or in the back. And then, is the initial solution optically active? Yes, it is. There's a chiral center here, which allows for optical rotation. and then the initial solution will not be optically active because there are two enantiomers and they are an even mix. Therefore, their optical rotation will cancel out because what is in the front and what is in the back, and their chirality is opposite. Therefore, there will be no optical rotation. So I believe that explained everything. I do hope it made sense. Please ask me if you have any questions. But if not, thank you for watching, and I hope this worked.